That is fantastic. Yeah, space gets everybody excited. I mean, we were talking about, that's one of the things I love about the Computer Museum is all the space-related exhibits, right? Whether it's the fictional exhibits of Star Trek and some of the different ones they have in the back, or have a really phenomenal Apollo exhibit here. And I was just looking at the Apollo computer display, which is super neat. I mean, how often do you get to see things like that? So anyways, my name is Zach Kowalski. I am predominantly, I am a crime scene detective here in Roswell. I'm going to shut that door if that is okay. A little bit about some of the research that we're going to look at today. It's been sponsored by a few different organizations, apart from my university and my agency providing laboratory space, the University of Louisville and their cardiothoracic research. And then that's my private company and doing some support through that.
Foxton is your product?
Yep, Foxton Forensic Science Laboratories. Let's see, we'll go back here. So Disney shot that for a video, a movie they did called Man in Space. That's in '63, I want to say. So that's 6 years before we ever put somebody on the moon, which is incredibly amazing. And obviously that is decades from now of the advances that we have made. I'm super excited about the Artemis program going back, right? I don't think we should have ever left the moon, but that is an opinion for another time. But the reason I show this is we have been looking at space research for more than half a century. Really, we've been looking at space research for centuries, right, of going back to Galileo. But the idea of how do you take something as unique of an environment as space or as microgravity or extraterrestrial environments, and how do we apply our thoughts and asking those investigative questions that we do here on Earth? Nope, we already did that. So first photograph of Earth taken in 1946 from White Sands Missile Range. Kind of just doesn't look like a whole lot if you don't know what you're looking at, but if you know what you're looking at, that is incredibly beautiful. So when it comes to microgravity research, contemporarily we use microgravity research for all kinds of stuff, from medicine and looking at the biomedical development aspects of what we can use here terrestrially. Taking away gravity gives us a lot of really unique perspectives, right? And so we can apply that to agriculture, growing tomatoes, and seeing how how gravity specifically affects the growth, right? How does it affect cellular development? And that's why it's really important in pharmacological research and agricultural research. And then the fluid dynamics component, right, is how do fluids act under the absence of gravity? That helps us understand how to design fuel systems, right, is because how fluids slosh can affect weight distribution and just every component, right? Gravity has such a perverse influence on us that we don't necessarily always realize that we take it for granted. And so that's why it's important to just research things. Research. So how do we conduct microgravity research, right? Well, one is there's the International Space Station, at least for a little bit longer before they bring it down. That is a laboratory that was built specifically for this purpose, right? And it's up there doing that. Or we can do exactly what his shirt says, right? The zero-G experience in doing parabolic flights. And what this is it's a specially built airplane. You go up and you're going in apogee and you're basically riding, it's called the vomit comet, right? And so that is another way where we can induce 15 to 20 seconds of microgravity per apogee to be able to have short-term experimentation. The other one that I don't have on here is drop tower. And so drop tower is just another way, it's going back to dropping a a feather and 10 pounds and seeing how gravity works, right? So drop tower testing is another thing that we can do. That now it's a lot more than just dropping things off of a tower. There's creating vacuums and
Very short.
very yeah. Whereas we have 15 to 20 seconds here, you're talking about less than that, way less than that, for drop tower testing. So predominantly within fluid dynamics, when we're talking about space research, is we're looking at pharmacological and those fuel systems. But space medicine is the most interesting component, right? Because your body undergoes a lot of really unique reactions when you take away gravity, right? So one of the things that I think is super interesting is just when we're looking at fluids, though, is that surface. It's a beautiful sphere, right? I think I have it in here. There's a great video of that. That's Mark Kelly's bald head. And he's doing some fluid dynamics demonstrations. I'm pretty sure we'll look at that here in a minute. But what happens, right, is so you undergo something called fluid shift, and it's where all the fluids start to pool to the core of your body, right? And so you end up with this atrophy of your leg tissue, and you end up with skinny leg, chicken leg puffy face syndrome is I think what it's called, right? And that's where you have your fluids are getting infused to your core and into your face, being drawn away from your extremities. And that happens pretty much immediately. And it's just the degree to which that starts to affect you over the course of 4 to 12 hours. During all of that, we have, it starts to affect your blood, right? The ratio of your plasma to the rest of your erythrocytes, like red blood cells and stuff like that. So it eventually does balance out. That's called your hematocrit. The ratio between red blood cells and your plasma is the hematocrit level. Typically, within most humans, it's somewhere around 40 to 42%, but that changes in microgravity. Thankfully, our body's really smart, and it balances it out over time to where it's not too much of a problem because we start excreting out all that excess. And then, it can affect your blood pressure, and basically it has a cascading effect on the body, right? Everything from the shape of your eyeballs to the loss of bone density, especially the longer that you're. Absolutely. No, absolutely. And think about it this way, right? So from a space medicine standpoint, which is where I really kind of took an interest in it, is how close is a hospital if something happens when you're on board the ISS, right? We're doing telemedicine, that's one thing, but congratulations, you're now the surgeon, right? I have this terrible wound that I've sustained from an accident. It's expeditionary medicine is what it is. It's just a different frontier. Yeah. I never realized until I really kind of started into the research of the degree at which you really have to plan. I don't think I had a good appreciation for it. I mean, it's just like, if you go camping, right? Like I need to have my first aid kit, do I understand how to make a splint? But at least there you can get life flighted out, right? If you're even in the remote Blue Ridge Mountains, you're really high up on the ISS, right? There's a lot more that goes into it. And especially with traumatic injury, you have minutes a lot of times if it is a breach of your cardiovascular system. So being able to, how do you address that, right? So Hollywood depicts violence in space really dramatically, right? And especially with lasers, and you have but what's interesting is that last Star Trek video, right? The Undiscovered Country. There's the scene where the ambassador gets shot by, the lasers, and you have this blood that is ejected, it's projected out into the environment, right? And you have these rotating globules of blood, when in reality, that's kind of actually what it would look like. That of all of the Hollywood fiction that's out there, Star Trek has the most realistic, and that's because they consulted, right? They had really great technical advisors. When I was talking to NASA researchers that I'll tell you all about here in a second, I asked him, I said, I'm looking for video that gives a really great representation of it. He said, look at Star Trek Undiscovered Country. It is by far the best representation. And so that's why I include it, because it really is, it's super neat. Even if I disagree with one major component of that, and that is the fact that we're using lasers, and lasers would cauterize the tissue. And so you actually wouldn't have a breach of the cardiovascular system. But with us becoming more of a spacefaring species, as we venture out, as we become more expeditionary into the solar system, the risk for traumatic injury is going to increase, right? Just like as pioneers ventured into the West and had to deal with broken legs and impalement and all that kind of traumatic injury, we're going to experience the exact same thing in space. But at least today, we have a lot better medicine. We can prepare for that a lot better. So what happens when you bleed in space, right? If you're an astronaut crew member and you got a wrench that you're working on, some kind of device inside the ISS, and the wrench slips and you cut your hand across a panel. What happens, right? What happens, because you're in microgravity at this point, and microgravity and zero G I'll use interchangeably. But what happens, right? Is the blood going to start dripping onto the panel? What'd you cut, right? Did you cut just some surface level capillaries, or did you hit an artery or a vein? That's a very good point, is what kind of pressure do you have? Well, if it doesn't have a whole lot of pressure, you're just going to start to have this mass that's going to start to accumulate, right? It's called a fluid dome. And it's just as we're supplying more and more blood into that dome, only then once we start having a shear force. So I move my hand really quick, right? Or something hits my hand. Once we impart that energy, then that's when you'll have the detachment of blood from your hand. So same thing. You and I get into a fight in microgravity, and I suck you really good, right? I'm drawing. Now I'm imparting some type of kinetic energy, and there's that transfer, so then we can start actually dispersing blood into the environment. So this is, what movie is this? This is another really great example. This is a more recent, The Midnight Sky from 2020 on Netflix. And they have a scene where they have blood within the atmosphere, or within the cabin of a spaceship. And they do a really, really good job. So they took Star Trek Undiscovered Country, and they did it way better. They did it with like 8K CGI, and it looks really good. But they got the surface tension values really well, right? So, and we'll talk about surface tension here in a second. So why is all this important? Why am I talking about this? Especially, why is a forensic guy talking about it? Well, I mentioned I'm a PhD researcher, and my research is in bloodstain power analysis. A few years ago, after I'd started my dissertation work, my area that I was looking at was how does the environment influence bloodstain patterns, specifically as variables, right? So we can take a bloodstain pattern, we've got it on a wall. We can measure that bloodstain pattern, different individual stains, take the width of it, the length of it, and because it's an ellipse, right? So when blood is projected into the environment, it wants to form a sphere. It's just surface tension, right? It wants to be the smallest possible version of itself. So because we know that it's a sphere, when it strikes a target surface, we know it's an ellipse.
Because when it touches it, it's going to have momentum, it's going to spread out into an ellipse.
That's exactly right. So we can measure that ellipse, the width and the length, and we can then backtrack the angle at which it struck. It's called the angle of impact. So how does, because that's so important for us in crime scene reconstruction to understand where the blood source was in space, in three-dimensional space, I should say, not space as in floating, but three-dimensional space, is how's your environment affecting that final stain shape, right? So what I was looking at is I was looking at surface roughness, you know, how does the micro-terrain affect it, as well as porosity. And I had this idea, because I'm, if you haven't noticed, a bit of a space nerd. It's like, I wonder how gravity, how would bloodstain power analysis work in space? How, if I was on a space station and I had some kind of violent incident, would I, as an analyst, be able to reconstruct that scene? And my hypothesis was absolutely, because we're removing gravity, so my formula, hey, go back, I'm not ready for all those. That one. So this is the formula I used, right? And this kind of gives you, this was debuted in 1938. And so we've been using it since the late 30s, right? And there's 39, excuse me, in Paris. It's taken in the absence of gravity, though. Yeah, so this is just basically using the shape of an ellipse, the size of an ellipse, to understand the angle that it's relative to. So it doesn't take into account air current, such as how extreme was the wind affecting the influence of the stain. Or, yeah, absolutely, or the surface roughness on which it struck, right?
So it doesn't take into account that the pathway of the droplet is parabolic.
It's parabolic. So this, correct, this is only looking at a linear concept, right? So that is one terrestrial downside of the formulas that we use is it's taken in a vacuum, right, without gravity. Now, lots of research has been done. Yeah, and without air drag, exactly. So there is a ton of research that has been done on specifically that, right, is what is the distance that a droplet will travel before air drag and gravity really start affecting a parabolic flight. And it's about 1.5 to 2 meters. So everything within, we'll call it 2 meters, it is linear, right? We don't have to worry about it. Our reconstructions are true. But once you start getting past that, then you're on the back end of that parabolic arc.
What does it take to make a blood droplet go 2 meters?
That's exactly right. Are we talking low force where I'm punching you, or are we talking high kinetic energy of a gunshot wound, right?
And then how far above the surface on which the droplet lands was the impact?
Yeah, and then the other component is oscillation, right? As soon as blood detaches, it wants to be a sphere, but it's not initially because it's detaching off of a wave. So it's going to oscillate to equalize those internal vortices first, and then you have a perfect sphere. And it's about 40 centimeters for it to travel after detachment for it to reach that. So now we're talking, 40 centimeters. So we want to be past 40 centimeters, but under 2 meters to have those perfect linear stains. But still, none of them takes into account surface roughness, porosity of your target surface, or gravity. And so that was kind of where I had, if I hit space, no. So that was the idea, right, is I had gone to my advisor and I said, hey, I have this crazy idea. I want to do a thought experiment. And I want to collect all of the space medicine research that's out there that understands and looks at blood in microgravity environments, and I want to be able to extrapolate from that and apply that to a thought experiment of bloodstain power analysis. How would it work? Because space medicine is an entire field, as you know. He said, sure, go forth. And so originally it was just going to be a literature review. That's all I was going to do. And I contacted a friend of mine who was retired from out in LAPD because she had a friend at JPL. And she said, I'll give you her contact info and you can reach out to her for literature. So I did. I said, hey, this is who I am. I'm looking for any literature or video material that I can use to extrapolate from. And so there we begin the cold. She's like, yeah, you should contact this person, who says you should contact this person, right? And so I end up getting in touch with a few NASA researchers who were specifically looking at fluid dynamics, and they proposed a few different good articles. And one of the articles they'd given me was by a space medicine researcher who looked specifically at cardiovascular issues and bleeding hemorrhage in space, and how do we contain hemorrhage. His name is Dr. George Panelos, and he's out of the University of Louisville. And so I cold emailed him. I said, hey, my name is Zach. This is who I am. This is who I'm looking for. I read a couple of your articles. They were incredibly helpful. I appreciate the images you included. Do you have any video of your research that I could use? Because what I'm looking for is I wanted to break down the videos frame by frame to understand what the blood drops were doing. He said, yeah, absolutely. I'm actually traveling to Kennedy Space Center next month to go do a parabolic flight and for our research. I could stop off in Atlanta and we could have coffee and talk. Absolutely. So George stops off in Kennesaw and we talked for like 2 hours. And we talked about everything, right? He's a very brilliant researcher. He's got a really cool experience. He's got more flight time on parabolic flights than I think anybody. And he asked, if you were to do this, if you were to do research and actually try and apply what you're looking at, how would you do it? And so on the back of a Starbucks napkin, I kind of sketched out, because what's interesting about parabolic flight research, and you understand this since you've been on one, is you have only so much laboratory space. It is incredibly confined, and you're competing with other experiments that are on board as well. So you really have to boil down your investigative question. What is the key thing, the number one thing that I am asking here? And for me it was, what does the shape and size look like in the absence of gravity? Period, that's it, right? So we want...
At what point, though, for how long?
Yeah.
You said it's going to change. It's going to be for the distance it takes to travel 40 centimeters. It's oscillating.
Yeah, and we only have 15 to 20 seconds to play in, right? So the thought was, well, I would probably just project liquid blood towards a target surface at known angles and then measure, right? And I want to be outside of that kind of that 40 centimeter mark so that I have the reduction of oscillation. And so I sketched out, I said, this is probably how I do it, and we talked our way through it. And he said, well, I tell you what, if I have extra time on my next flight, I'll do it. Really? Okay. And he said, just send me the material that you want. So I mailed him the material and
Build the box in which it's
so I was hijacking off of his box that he was using, because his research was specifically looking at, and he's got a lot of great publications, is when you're bleeding and you have that fluid dome, it's very difficult to do surgery because blood's in the way, right? So same thing that we kind of do here on Earth is vacuum, right? Is suck it away. But what's the best way to vacuum that material out? So he's already got enclosed containers. And so I sent it to basically the same paper that I was using here, and just super simple. And unfortunately, that December flight, he didn't have time to do it. No worries. It was a great thought experiment. But then I get a call from him on May 5th of the following year. He said, hey, I have great news. I was able to do 2 trials. I got you 2 targets to actually work with and the video. And that would have never happened if I hadn't asked the question of, is this possible, right? Or just put yourself out there. Cold emails, that's all where this started from. And then next thing I know, I've got 2 really cool targets that have blood that were produced in microgravity. I've kind of blew past all this. Yeah, so here's Hatfield on ISS, and he's doing just fluid dynamic demonstrations, right? And just, it's really, and this was all I had planned on doing, right? Is I was just going to take a bunch of the videos that he and Mark Kelly had made on ISS and understanding how the fluid droplets are detaching, right? Is what's their course, what their linear trajectory, how much are they oscillating? Looking at that, breaking all of it down as much as I can to extract as much information and synthesizing that information and applying it to bloodstain patterns. Is theoretically, how would it work? I think it would work based off
What's the difference in viscosity between blood?
about 1.6. So if water is 1, blood is 1.6 in terms of relative density. The concepts, though, of dealing with fluids is really what I was looking at here. This is one of my favorites because here is Kelly with, those are hydrophobic paddles, right? And so he's just got this sphere of, yeah, space pong. That's exactly right. Boop, boop. But you can see the oscillation there, right? It's amplified. It's the same thing that happens here. It just,
Starts new oscillation every time he touches it.
yep.
So it could compound or it could cancel.
Yeah. How cool is that, right? And so at that point, you know, that's at scale. That's a pretty large, that's a golf ball size fluid, right? When we're talking about blood terrestrially, we're talking about very small stains, right? You know, the 3, 4, 5 millimeters in width. But the concept applies both ways. So this is a really great example of surface tension of that fluid, right? So the same thing, they're lighting it with, they've got some underlighting going on.
So that's just water.
Yeah, it's just water. And look at how perfect of a sphere it is. This is the best example of surface tension that I think you could ever show.
It's so cool with the little droplets
It is.
around to it as well.
So yeah, I kind of already dove into this, but it just started with a cold email. And what would eventually end up would be this. So we're not using human blood here. This is an analog just because of health hazards. You couldn't do it on board. So we're using a glycerin analog. So I think it's 40% glycerin. But what's cool is so that's what you get, right? We did that twice with 2 different targets. And then we take this video, we extrapolate, we correct for the distortion, the fisheye distortion, and then we break it down frame by frame and understanding what each individual droplet does, and then
It's just out of a little syringe.
it's out of a little syringe.
CC.
Yeah, that's it. And so then we take as much information from that as we possibly can.
And it's hold it about 45.
Yeah, so this is actually 45 degrees, so he does 2 shots. One's at 45, one is at 55. And then there will be a moment after this frame, he ends up turning it flat towards the camera, and it's from that where we actually start measuring all of our information from. Because you know, as soon as there's about to be, in 5 or 6 seconds, it's 2G, and we lose all of our stain shapes. So there's no way to preserve it. You have to do everything from frames of the video.
And then your measurement it's dependent on understanding the angle too.
Yeah.
The distance is not simply linear, it's at an angle.
Right. So there's that, and obviously we can't use, this doesn't really help us. We're using the small individual stains and measuring those to start understanding those angles
And
of
the video
impact.
can give you an indication of when it hits, how much of it is sliding across
Yeah.
versus just sticking.
We can literally break it down frame by frame. And that's one of the great values of taking, this is a pretty simple experiment. All in all, this cost, just the materials is about $5, right? It's that $40,000 flight that's the problem. So yeah, a $5 experiment that we're able to apply novel research to. And that's kind of the cool thing when I go back to saying you really have to break down what is the investigative question of your research at bare bones.
It looks like a piece of foam.
Yeah, so it is 50-pound butcher paper that is mounted on foam board.
And you did butcher paper because you knew the porosity?
Yeah, because it's the same thing that we use here on Earth, right? So butcher paper is a pretty standard target that we use in bloodstain research. And so we just use the same thing because I already have sample sets here. So we're going to talk about that. So we take the individual frames, and then we would bring them into a bloodstain program called Zone 3D. That's where we do all of our ellipse marking, and it's going to give us our measurements and our angles. And then from there, we see what else can we extrapolate, right? So there was you have several that end up, it's called secondary spatter, where it's coming out, it's blood going into blood, and they have these beautiful straight linear trajectories, right? And it's just another great example.
And you say secondary spatter, that's like,
It's blood hitting blood, and you end up with,
it's blood hitting blood, or it's when it hits the surface and then sprays off of that?
yeah, both. Yeah, it's same thing. We just call it secondary spatter is all.
And you need to distinguish between those two things because the secondary spatter will give you a line back to the origin point.
Correct.
Does the secondary spatter change the momentum of the initial? Like when it adds, does it add more?
Yes.
You can see it bouncing off and going up past,
Mm-hmm.
like getting on his plate.
Yeah, it gets on the cuffs of his.
Yeah, and you see the little dots go shooting across the screen, and it's like,
Yep.
hey,
Off it goes.
frame now.
But what I found really,
Glove box?
yeah, it's a glove box. It's a pediatric glove box, is what it is. It just modified. So what this is such a great visual representation of, though, because you pointed it out, is some go up here, some go up there, it is that radial distribution expanding out, right? Not just, in a two-dimensional, but we're really seeing a great example of three-dimensional spread.
Yeah, and microgravity is like tracing back the comets,
Yes.
single point.
It's just Newton, right? It's just inertia at work. So we ended up publishing earlier this year in Forensic Science International of our findings. And ultimately, there were two key findings out of it. The question was, like I mentioned earlier, my hypothesis was that it was going to be just as accurate because gravity is being removed, and so you're going to have really true, accurate stain measurements and angle of impact measurements. I was wrong. I was 100% wrong. And it was the coolest thing to be wrong about, because what ended up happening is, while you can still, you still have this ellipse that's being made, so you can still understand the direction that the stain was traveling, so you can identify directionality, but surface tension starts taking over and you don't have as much spread. So it's inhibiting the fluid spread, and because of that inhibition, your width and your length are shorter, which means that our formula doesn't work the same. So where it might be, where here on Earth it hits 45 and you're able to extrapolate, yes, it's 45 degrees, because it has a complete spread. Because of surface tension, it doesn't completely spread. It actually is shorter. So
The microgravity means the surface tension has a higher impact.
yes, a higher influence. It's amplified because gravity is not, taking hold.
So you keep the same total of forces, but because the force of gravity is not there, then the other forces take over.
That's exactly right. Couldn't have said it better myself. And so that was the super unique thing, right? So this is the first research that's been done of looking at forensic concepts in microgravity. And so that's kind of what's the next thing you can So we published in March or in February, and it kind of got picked up everywhere. It was very cool, and everyone wanted to talk about the first murder in space. But the past year has been super neat. I just had an interview with a publication out of Germany yesterday. But there's interest all around the world in this, and that's the most exciting thing for me, is the concept of taking something as novel as astroforensics and applying how can we look at all the different forensic disciplines. Because fast forward a couple centuries from now, we will be a spacefaring species. We will have violence, and because where humanity goes, so too will human behavior. And human behavior is incredibly violent.
Whether it's microgravity or reduced gravity at 1/6.
At 1/6, yep. Or even amplified, right? Even more. I don't know.
That's where we're going with it.
I know. I don't. Hey, right? Once we really start getting outside of our solar system, once we can master that whole faster than light speed.
Certainly on the moon or on Mars.
Right.
Or in microgravity on some way.
Yeah, and so I get when I first approached my advisor about this in 22, he said, "Well, I'm all about it, but a lot of the advisors in your defense board are going to ask, what's the practical application?" Excellent question. I'm so glad you asked. Right? Consider if we had a catastrophic event on ISS today, right? And we needed to understand failure and where crew members were at specific points, right? If there was injury, we can apply some bloodstain patterns. You know, we look at here on terrestrially, one of the things that gets overlooked for bloodstain is on crashes, and how we can use bloodstain patterns in vehicles to understand, was the driver wearing their seatbelt, right? Where were certain people at the time of this event? We can take the exact same concept of accident reconstruction and just apply it to a space vehicle. So that's kind of the practical application, apart from also understanding those physical forces and having a better understanding of how surface tension really is a secondary predominant factor of stain spread. Here on Earth, it's just being muted by gravity. So that's the practical application of it. The nerdy version of me is because we want to understand how to solve murders in space, okay? And that's kind of the novel idea that came from it is how will forensic science work in space, right? So bloodstain pattern analysis, modern research has been around since about 1854. So a little over 160, 170 years that we've been looking at bloodstain patterns and understanding mechanisms and physiology behind it. And we see where we're at today. Think about where we're going to be at 200 years, 300 years from now. It's got to start somewhere. And how is it going to apply to other forensic disciplines? What does the space environment or the extraterrestrial environment offer for those? Big thing for me that I'd love to see research on is DNA, right? Is how does cosmic radiation affect DNA and the ability to amplify and type DNA to a known source? Or does the radiation degrade it so much that we can't do modern day amplification? We have to kind of come up with so amplification. If I swab something, I want to create copies of it, right? It's called PCR. And I want to make more and more quantity, because I may just get a little bit of DNA, but I want a lot of DNA to work with, right? So we have to amplify that DNA, and we do through a process, then we can type that profile. How does radiation affect that, right? Same thing down in fingerprints, right? So we see on TV fingerprint dusting. I dust for fingerprints all the time. Can you imagine dusting in 0G? The powder would get everywhere, right? So how do we process for fingerprints? We would probably use something like a vacuum, right? There's several different chemical applications such as cyanoacrylate or superglue, turning it into a gas. We could fume the fingerprint in a sealed, put a suction cup over it, right? Yep, and then be able to extract that toxic gas and process it that way.
Yeah, because they don't want powder.
No, absolutely not. I hate powder here on Earth. It gets everywhere. It is like the glitter of forensic science. I look like a chimney sweep after I have worked a really extensive scene.
And the DNA, when you say destruction of DNA.
But yeah. Right? So cool. Little known fact, that was actually filmed just outside in the Apollo exhibit. So there's my contact info. You can find me at all those different places and whatnot.